So let's see how to detect faces and actual facial features, so eyes, noses, mouths, that kind of thing, inside of images of actual human beings. Not just actual human beings, stable diffusion generated human beings too. So let's move on. Here you'll see the notebook, and I've got a link to this in the description of the video. But I start out basically by detecting Colab. I do write all of these to be Colab sort of first, but you should be able to run it on other platforms. I also put in connections for CUDA and for Apple. Now this one will give you an error if you're not using CUDA, because the underlying packages are designed for CUDA, at least currently. I'm seeing more and more support for Apple all the time. But here we're going to focus on detecting facial features from individuals. So where are their eyes? Where is their nose? You can do all kinds of stuff with this. You can do facial alignment, where you are processing a lot of images and aligning to certain things. You can recognize emotions. We'll see how to do that in a moment. You can do face morphing and animation. I mean, think TikTok, WhatsApp, all these things where they're putting stuff on your face or transforming your face. We'll see how to put eyeglasses on a face, at least in a simple way. Animation of your face, gaze tracking, and many other applications. I'll even show you a medical application that I've worked on some. Hopefully eventually have a paper out on that in the future, but that's coming up as well. So here we are going to install FaceNet and SGIPA. So FaceNet we saw before, that's going to find the individual faces. SGIPA is going to actually find the features. So this comes from this paper, Shape-Preserving Facial Landmarks with Graph Attention Networks. So this is a paper that was put out not that long ago, and this is currently the state-of-the-art or the near state-of-the-art in detecting facial landmarks, even without bias. So I make use of some of the stuff where I'm working with medical research and we're dealing with neurologic issues where maybe somebody doesn't blink symmetrically. Before this was out, a lot of the neural networks were quite biased, and if a face was not completely straight, it would try to fix it for you, which is a misclassification. That is bias in neural networks. There's many, many types of bias, but that is one. In this paper, they talk about how to really preserve the actual shape of the face as they go through it. I'll leave a link. I have a link to the paper in the GitHub code that I shared with you. The authors of this paper were also wonderful and put it on to GitHub as well. So if you look at some of their examples that they have here, this is amazing. You can see that the person is moving their face around, and you can see it's also tracking the three-dimensional Euler angles of his face. So you can see the pitch, roll, and yaw, to talk about it like an airplane, of his face as he's moving it. You can also see even these individuals. I don't even know what these individuals are doing, but whatever they're doing, it looks really confusing to a neural network, and it's handling it awesome. What is this guy doing? This is a great video. It's from the slow-mo guys. I highly suggest taking it out, but they decide what happens if you smack a guy in the side of the face with a soccer ball. I had that happen a few times in school, not intentionally. This was intentional. But notice the dots on his face. His face is contorting all over the place, and it's maintaining it. That is not what a face normally looks like. As soon as I saw that, I thought, okay, this is what I need to work with for some of the neurologic issues of the facial nerve with certain researchers that I collaborate with. More on that later. So anyway, we install SGIPA and we install FaceNet. And now we're just going to load the image that we're dealing with. We're going to deal with an image of me. Why not? I don't have to get permission. And I set up the MTCNN, and we're going to find first just my face. So we find my face, and this is using just PyTorch-facenet. You can see it here. You can see there's some false positives. I don't know, that book. Maybe there's a face behind there peeking at me. I don't know. And then there's other false positives there. There's a face growing in my beard too. But nonetheless, you can, if you're dealing with just one face, you can pretty safely usually just take the first rectangle that it's given you. So what we're going to do now is extract this face, mine, and we're going to put it into a bounding box. So we get the 4 points from this. We do have to convert these to integers because mtcnn does give these pixels back as floating point, just due to the imprecise nature of neural networks. It's not like they can be floating point because pixels are discrete values. So, but nonetheless, you've still got to convert this to all integers, and then we create the bounding box. We're going to load the image and load the image from the URL. So this actually reloads me so that I can be in the other format because it does require it in OpenCV NumPy format. And then we process it for the actual facial features. When you display it, first of all, just look like here, you can see these small green dots. Those are the individual facial features that it's finding. You can see my pupils and my eyes. You can see where my mouth is. Facial hair is not even messing with this. I've seen some of the older ones, facial hair messes with it. Nope, works really quite well. And what becomes important as you make use of this is you have these facial landmarks, and these are fairly standardized. So you can see this individual here. I actually created this. So that's a Stable Diffusion person who volunteered to release rights for me to reuse their image. And you can see all of the points. So if I wanted to know where the tip of this person's nose is, it's always facial landmark 54. The pupils are always 96 and 97. That'll be important in the next video when we start dealing with medical applications of this, where you're analyzing nerve palsy and other issues where one side of the face doesn't do what the other side of the face is doing. Facial paralysis is a medical application that I have worked with directly on this one. So what we do here is we simply loop through and display them all. Actually, we don't even do that. We use the plotter, which is something that the authors of SGIPA gave us, and we just basically automatically put all of these on there. Usually I am not using the plotter like you see here. The plotter can put those landmarks on quickly, put the head pose on. Usually I want to do my own stuff with it, but for now, this just lets you see that yes, we can indeed get this here. I put the bounding box, also that the first neural network detected when it found my face, and then these landmarks come from the second one of my face. So that is how you can detect the facial features for somebody. And this is a very handy lookup if you're using SPIGA to deal with this. There's different standards for these. These don't all have the same numbers, and they don't all have the same number of facial features. SPIGA has 97. Thank you for watching the video, and if this was useful, give me a like, subscribe so that you don't miss the rest of this course, and hang out for the next videos because we're going to see how to detect emotion.